Hi, and welcome to this Java screencast. My name is Andy, and today I'm going to talk about the synchronized keyword and what to consider when using it. So, what does this keyword actually do? Well, the idea is pretty simple, and to show you, I've built a small sample program. It is called unique number generator, and it will create a unique number for each call of the next method right here. The internal implementation is pretty simple. We just increment our internal variable so that an ascending number will be created on each call. To test our implementation, I have an endless loop here, which calls the next method frequently and compares the result against a set, which is defined up here, and checks if the value has been seen already. In this case, our unique number generator failed and we output a message. Otherwise, we just add it to the test set. In a single-threaded environment, this implementation will work fine. But in a multi-threaded environment, this might fail because the increment operator of long is not atomic. So if I start some threads, like I do here in the main method, we will see collisions of the unique numbers. And as predicted, as soon as we start the program, we see lots of duplicate numbers being generated. To prevent that, we can add the synchronized keyword to our next method, and this will guarantee that only one thread at a time can enter the next method, and therefore we will have atomic access to our number variable, and our unique number generator will work as expected. Now if we start our program again, we see that no duplicate numbers are generated anymore. So now that we've seen how to use the synchronized keyword to enforce the correct behavior of multi-threaded programs, let's talk about the performance implications. And to better show this, I've created another example program, and this has a main method which again starts two threads, one up here and one down here, and each of these threads has an inner loop which frequently calls an increment method. One calls increment A and the other one calls increment B. And what these methods do is having an inner loop which counts from 0 to 10k, and the increment A method increments the variable A, and the increment B method increments the variable B, which are both defined up here. Both threads run 100 iterations, and they call the increment method until the counter reached 100 million. And we keep the runtime, how long it took to count up to that 100 million, in an average, one for A and one for B. So now let's run this program without any synchronization. This isn't required because we access different variables from different threads, so it's all perfectly fine. And as we can see, it took an average of about 9.4 milliseconds to count up to this 100 million limit. So now let's add a synchronized keyword to the increment A and leave the increment B unsynchronized. Now this will be interesting because the synchronized keyword has quite a bad image, because in its early implementations it had quite an overhead for locking mechanisms, but the modern JVMs can optimize that away, especially if only one thread accesses the method at all. So now that we've run the program again, we see that the runtime of the A part didn't change at all. In this case, it's even a bit faster. So as I've said, if only one thread accesses the synchronized block, there's nearly no overhead at all. Now if we add the synchronized keyword to the increment B method, we expect quite the same behavior, because each method is only called by one thread, and also all internals are strictly separated. There's no cross communication between the threads. So let's add the synchronized keyword to increment B. Now, as we can see, the runtime doesn't match our expectations. It has almost doubled compared to our first call. Now, in order to understand and inspect what's going on, I have rewritten the program a bit. As you can see, the synchronized keyword can not only be used as a method modifier, it can also be used as a block. In this case, we not only put the synchronized keyword in our code, but we also have to define on what we want to synchronize. We can use any object around to synchronize on. And the idea is that only one synchronized region can be entered by a thread for each object. So in our example, which is the equivalent implementation of putting the synchronized keyword as a modifier on a method, we use the synchronized block on the this instance in both methods. This explains why the runtime suddenly slows down, as only one of both methods can be entered at a time. Now the question is, can we do better? And the answer of course is, yes we can. Because instead of synchronizing on this, we can synchronize on any other object. And as it so happens, we have two distinct objects just here, our average A and average B. The type and the purpose of the object doesn't matter at all. We just have to agree on what we want to synchronize. So if we put our average A in here and our average B in here, we can recompile and rerun the program. And as we see, we are back to normal performance. So what's the takeaway here? Well, basically, first of all, as we have seen, a synchronized keyword itself isn't that bad. A method which is mainly used by one thread at a time isn't slowed down by the keyword at all. However, watch out for having multiple synchronized methods in a single instance. As we have seen, even though our threads could have accessed our methods in parallel, they didn't, because the object was always locked completely. Therefore, always prefer short synchronized sections which can be easily overlooked. Also, have a look at the java.concurrent package, which provides a lot of tool and helper classes for concurrent environments. And one of them is shown here, which is the log interface along with a default implementation called reentrant log, and this is the modern version of a synchronized block. As we can see in our increment methods, a log is as easy to use as a synchronized block. You obtain the log by calling the log method, which waits until the log is free, and once you have obtained the log, you can enter the critical sections, and you can release the log by calling the unlock method, which should be always done in a finally block. Now the benefit of using the log interface is you can exchange the log implementation based on your needs. Also, the interface defines some more functions which are quite helpful, like a try log method, which only enters the critical section if the log is currently free, and it will not block your running thread if the log is already acquired by another thread. So I hope you have enjoyed this quick screencast about the synchronized keyword. If you like it, please give it a thumbs up and catch you next time.